Let's take a look at trig in 3 dimensions, three-dimensional problems. And sometimes it's really hard to get your head around a three-dimensional problem, and so it's easier to just redraw pictures in 2 dimensions. Just how we're used to seeing it on paper, I guess, is in 2 dimensions. Now, you might need to draw some triangles that aren't necessarily drawn in the original diagram. You have to create some new triangles. But really, there's 2 key ideas in 3 dimensions. Finding an angle between a line and a plane is one of those ideas. We'll use this as an example. We've got a cone, base diameter of 18, slant height 15 centimetres. We want to find the angle that that curved surface area makes with the base. So this would be an example of a line and a plane, the base being a plane, the line being, for want of a better word, one of the edges of the cone, if you think of it as having an infinite number of edges going round. But that gives us the line that we're trying to make the angle with. So how do we approach it? Well, I want to drop a perpendicular from any point on that line to the plane. Now, it makes sense to drop it from a point where we know the length of it. So I'll go right from the top here, the vertex down. Then I'll join the point of intersection of the plane over to the other end of the line, which in this case we've got anyway because it's the diameter of my cone. This creates now a 2-dimensional right angle triangle. That has to be 9, of course, it's the radius, and a simple bit of trig, we can work out the angle. That's one thing we might have to do, find the angle between a line and a plane. The other thing we might have to do is find the angle between 2 planes, so where 2 planes meet. Now, 2 planes will meet at an edge rather than at a point. We're going to find the angle between 2 of the adjacent faces in a regular tetrahedron. How do we do this? Well, from a point on that line of intersection of the 2 planes, we have to draw perpendiculars along both planes. I'm going to use BC as my joining point of 2 planes, the plane being ABC and CBD, the other one down the bottom there. It makes sense to draw the perpendicular to go through the vertex up here because I'll be able to find that length. It also will mean that the perpendicular along the base will go through D. But I've now created a 2-dimensional triangle that I can work with. That's the angle we're trying to find. This is one where maybe it is easier to draw this in 2 dimensions, but basically there's the triangle. It's AED. I know that the length of AD is A. I'm trying to find theta. So I now need to find another side. If I just look at, well, I've gone for the face ABC here. So that's what we've got. I know it's a regular tetrahedron, so that angle must be 60 degrees. Simple bit of trig, I can work out that AE then must be A root 3 on 2. Whether I use trig or just the ratio of sides in a 30-60 triangle, because we know that ratio is always going to be 1 to root 3, however we choose to do it. But I've got that length AE then. I'm actually going to use the cosine rule to solve the problem. I mean, I could have divided that in half and made a right angle triangle, I suppose, and used right angle triangle trig, but cosine rule is going to be easier because I know that AE and DE are going to be the same length because it's a tetrahedron, everything's lovely and symmetric in it. Plug it into the cosine rule, those that recall it. Now I'll have 3a squared on 4 plus 3a squared on 4 minus a squared over 2 times a root 3 on 2 times a root 3 on 2, which gives me that cos theta is a third. I have my angle that I'm looking for, 70 degrees, 32. So really, it'll be either one of those 2 situations in 3 dimensions. Let's have a look at this very old HSC question. The survey is at point A. It's due south of this tower and it has height H. Angle of elevation when they look up at the tower at point A is 45 degrees. But then our surveyor walks 100 metres due east over to B, and then she looks up and the angle is now 30 degrees when we go to the top. And they basically want us to find a few things. We want to find the length of OB in terms of H. Alright, well, I've got a right angle triangle there that involves H and OB. Makes sense to work with that triangle. We want OB in terms of H. So OB over H will be tan 60. H tan 60, I suppose I could have even said, because that's one of our exact values, tan 60, root 3. I could have said root 3H as well. But anyway, there it is in terms of H. Okay. show that h is actually 50 root 2. Now if I go back to my diagram, I've got another triangle that involves h as well. So this one on the left, triangle AOT. Let's have a look at that triangle. We've got a 45-degree right angle triangle, so it must be isosceles. I know AO is also h. That didn't really help me to find h is 50 root 2. Let's go back, there must be another triangle. Well, let's have a look at the base then, down here. Triangle AOB, it's also a right angle triangle because that was due east. Let's see what we got when we draw that one up. OA we've said is h. They told me AB was 100, and we also worked out that OB was h tan 60 or root 3h. Bit of Pythagoras, I can now work out h. And hopefully we get, eventually, there it is, yes, we do get 50 root 2. There's our answer. The final part of that question. We'll calculate the bearing of B from the base of the tower. The bearing of B from the base. So we're going to put the compass at the base, which was O. And there's that triangle we were just playing with. But we now know that's 50 root 2. We've got to find the bearing. So it's that angle in there. I'm going to go for a true bearing. Well, I just got to work out angle AOB then. Subtract it from 180. We'll have our bearing. Simple trig. 100 over 50 root 2. We get 54 degrees 44 minutes. Therefore my bearing 125.16 is our bearing on that one. So all sorts of trig problems, but now we're dealing with things in 3 dimensions.